I'm very happy that Youngho is giving a talk today, and he will talk about the joint results with Robin. So,
okay, thank you, Liana, and to the organizers of this conference for making this happen and giving me the opportunity to speak here. So first, let me start with the underlying motivation for our results today, even though it won't really be necessary to state our results. We'll just start with the motivation, and that is linklessly embeddable graphs. So it's a topologically defined class of graphs. So a linkless embedding of a graph is an embedding in R3 such that when you take two disjoint cycles, they never form a non-trivial link. And by non-trivial link, we mean in the topological sense, where the two cycles or the two closed curves, they link through each other. They cannot be taken apart by an isotope. Okay, and in many ways, this is a very natural sort of topological, sort of the next step, three-dimensional analog of planar graphs. So let me try to convince you of that. So for example, planar graphs are obviously linklessly embeddable. You just take a planar embedding. But also apex graphs where there is one vertex, such that after you delete one vertex, the graph becomes planar. Those graphs are also linklessly embeddable. Okay, so you just take a planar embedding of the whole graph except one vertex, and you just add an apex vertex. It turns out to be linklessly embeddable, but there are other graphs that cannot be obtained this way. Okay, so we say that a graph is linklessly embeddable if and only it has some linkless embedding. And there are actually several different ways to characterize this family of graphs. So a classical result of Robertson, Seymour, and Thomas from 1995, they give two other ways to define this class of graphs. So one is just a slight variant of this topological definition. So a flat embedding of a graph is an embedding in R3, such that if you look at each cycle, you can fit some disk, embed some disk in R3 with the cycle as a boundary, such that the disk, the interior of the disk does not intersect the remaining graph. So obviously, if you have a link, if you have two cycles that form a link, then a flat embedding is not a flat embedding. You cannot put a disk on either of these cycles. So every flat embedding is automatically a linkless embedding, but a linkless embedding is not necessarily a flat embedding. So these are slightly different notions, but it turns out that the property of admitting some flat embedding is equivalent to admitting a linkless embedding. So a graph is linklessly embeddable if and only it has some flat embedding. Okay, and there is another characterization that it has no minor in the Peterson family. So let me first discuss what this means. So a minor operation is where you can delete vertices and delete edges, and you can also contract edges. These are the minor operations, and it's easy to see that when you delete vertices or edges, you cannot create new links. And also when you contract edges, you also cannot create new links. So linkless embeddability is preserved by minor operations. Another operation that preserves linkless embeddability is what is called the delta y and y delta transformations. So a delta y transform is you take a triangle and you add a new vertex in the middle. You replace a triangle with this cubic vertex. And the y delta transformation, you just go the opposite way. You take a vertex of degree 3, you turn it into a triangle. Okay, and again, it's easy to see that this cannot introduce new links. So linkless embeddability is preserved by all of these operations. Okay, and here's another fact that the complete graph on 6 vertices is not linklessly embeddable. And this is actually not so easy to show, but it is true. There's some algebraic way to show that any embedding of K6 in R3, you can find some pair of disjoint cycles or disjoint triangles whose linking number is an odd number.
Sorry, what are minor operations?
So minor operations are where I can delete vertices or edges or contract edges.
Okay, thank you.
So you're sort of making the graph smaller, but you're not introducing any new links. Okay, so just putting these together, these three facts, we know that K6 is not linguistically embeddable. So any graph that has a K6 minor, if you can somehow obtain K6 by minor operations, then that graph is also not linguistically embeddable. Similarly, if you have as a minor any graph you can obtain from K6 by these delta y and y delta transformations, that graph is also not linguistically embeddable. Okay, so first of all, what are the graphs that you can obtain from K6 by these transformations? And this is exactly the Pearson family. So it turns out there are exactly 7 graphs that you can obtain from K6 just by applying the delta y and y delta transformations. And it's called the Pearson family because it includes the Pearson graph. And these are the 7 graphs that you can obtain. Okay, it also includes K44 minus an edge and a few other graphs. Okay, and the result, the theorem of Robertson, Seymour, and Thomas is that a graph is linguistically embeddable if and only if you do not have one of these 7 graphs as a minor. So it's an exact characterization that it's to check whether or not the graph is linguistically embeddable, you just have to check that you don't contain one of these 7 graphs as a minor. Okay, so this is a very nice structural result. And from a structural point of view, this is, again, sort of a one-step up analog of planar graphs, right? Because planar graphs can be characterized by not having K5 and K33 as a minor. So this is a nice analog of that. Okay, so this is a theorem, but these are just 3 different ways to characterize the same family of graphs. And let me just mention there is another characterization called the Verdier invariant. So this is a parameter or an invariant that comes from differential topology, and somehow it's a very intriguing parameter. So let me just quickly describe what this is. So here's a definition. I won't write out the full details, and I really, to be honest, I don't completely understand the parameter all that well, but it's the maximum multiplicity of the second largest eigenvalue of the weighted adjacency matrix, where you take the maximum over all positive weighted, edge-weighted matrices. Okay, so don't worry too much about the definition, but it comes from some study of differential geometry, where you have this Schrodinger operator on some Riemann surfaces, and it turns out you can sort of approximate a surface by graphs that have certain parameter, and this maximum multiplicity of the second largest eigenvalue turns out to come into play there. Okay, but this parameter gained a lot of interest in the graph theory researchers because of these characterizations. Turns out it has very nice topological properties. So this parameter is 0 if and only if it has no edges. That's sort of trivial, but it has parameter at most 1 if and only if the graph is a disjoint union of paths, and at most 2 if and only if the graph is outer planar, and at most 3 if and only if the graph is planar. So this sort of weird algebraic condition here somehow captures topological properties of graphs. So it's a very intriguing but mysterious sort of parameter. Okay, and it turns out this also extends to linguistically embeddable graphs. So the forward direction, it just follows from the previous characterization as the 7 graphs in the Pearson family, they all have this parameter at least 5, which means any graph that does not have any graph with this parameter at most 4 is linguistically embeddable because it doesn't have those minors.
Sorry, what is outer planar? Outer planar.
So okay, outer planar means it's planar, but you can draw a planar embedding where all the vertices are on the outer cycle.
Thank you.
So yeah, the forward direction just follows from the forbidden minor characterization, and the reverse direction was proved by Lovász and Schreiber in 1998, which is a very nice result. So again, if we believe that this parameter somehow captures some nice topological properties, then again, linguistically embeddable graphs are in a way a nice or a natural extension of planar graphs. Okay, and here is an ambitious sort of conjecture that Colin de Verdier made, that so it's sort of an extension or an analog of Hadwiger's conjecture, that if your parameter, if this parameter is at most k minus 1, then the graph is k colorable. You should think of this as saying the analog of Hadwiger's conjecture, which says that if you have a complete graph on k minus 1 vertices, well, if you don't have a complete graph or on, let's say, k vertices as a minor, then you're k minus 1 colorable. That's the analog. Okay, so that's just one more way to characterize this family of graphs, and this is mainly just sort of try to convince you that this is an interesting family of graphs to study. It has these very nice mathematical properties. So now let's get into what can we actually prove about these family of graphs. And it turns out not much is actually known about. It's hard to actually prove things about this family of graphs, other than like these very nice characterizations. So first of all, probably the most basic question you can ask is, okay, what is the maximum number of edges that a linklessly embeddable graph has? Okay, well, let's look at the planar case. So in the planar case, we all know that planar graphs have at most 3b minus 6 edges, and this just follows from Euler's formula. Okay, but we don't have an analog of Euler's formula for linklessly embeddable graphs, and it would be very nice if somebody could come up with some sort of a three-dimensional analog that works nicely with linklessly embeddable graphs, that analog of Euler's formula, but we don't have such a thing. So we cannot really look at this proof and try to generalize this proof. We just don't know any analog of Euler's formula. Okay, but we can actually prove this edge bound, this extremal function for planar graphs another way. And this is a theorem of Motter, that for some small values of p, a graph with no kp minor that is not too small, it satisfies this extremal function where the number of edges is at most p minus 2 times the number of vertices minus some constant. So we know that planar graphs do not have k5 as a minor. So if you just plug in 5 for p, we get exactly 3b minus 6. So we don't actually have to go through this topological Euler's formula. We can get the extremal function for planar graphs just by looking at the complete graph minors. Right, so that's the result. Okay, and also if you just plug in p equals 6, we get that the number of edges is at most 4b minus 10. So immediately from the excluded minor characterization, we obtain that linklessly embeddable graphs also satisfy this extremal bound. Okay, and this turns out to be tight. So the tight examples are you just take planar triangulations and you add one vertex adjacent to every vertex in the planar. Turns out to be tight. Okay, and you can keep going. K7 minor, you get this bound. And now you might ask, why does it stop at 7 here? Why can't we keep going? And it turns out this linear bound is actually not the right asymptotic behavior, because it was shown by Bolobash, Catlin, and Erdős in 1980 that graphs with no kp minor, asymptotically, they can have the right number of edges that it can have is p times square root of log of p times the number of vertices. So this linear bound has to break down at some point, even though it holds for these small values. And I should also mention that a big part of the interest in studying these extremal functions also comes from this Hadwiger's conjecture, that graphs with no kp minor are p minus 1 colorable. And until very recently, the best known bound on the chromatic number of graphs with no kp minor just came from these bounds on the number of edges. Until very recently, and then there's been some recent results of Song, Norn, and Postel that finally broke the barrier of this degeneracy. Okay, so that's just a side note where why people study these extremal functions. Okay, but it turns out actually as soon as you go above 7, the bound breaks down. But Jorgensen showed that actually there's only one kind of a counterexample. So 6b minus 21, this is exactly what you would get if you plugged in p equals 8 here. Okay, and it turns out if you have no k8 minor, you also satisfy this bound, except for this one class of graphs, which I won't defined, but if you take the complete 5-partite graph with 2 vertices in each part, it turns out that graph has no K8 minor, but it violates this inequality. But you can also glue together these graphs to get more counterexamples. Okay, and you can push this a bit further. So graph with no K9 minor also satisfies this Motter bound, and there's this one example, counterexample, and one more special graph, both that are the exceptions. Okay, and we can go a bit further. So Robin Thomas and another student of his, Zhu, they are working on, or they have been working on, proving or pushing this further. So no K10 minor, you also satisfy this bound, and they're working on characterizing what the exceptions are, but there are a few more. Okay, but sort of the pattern or that we see with all these exceptional graphs is that they're all sort of, you obtain them, they're either very small special graphs, or you get bigger graphs by just taking the small graphs and you glue them together in some small vertex sets. So a conjecture of Seymour and Thomas is that if you impose high connectivity in the graph, then this Motter bound should really be the right bound. So in other words, the only counterexamples to this bound come from these small constructions and gluing together these small constructions. But this is also still right. So that's pretty much what we know for the extremal functions for excluding certain minors, complete graph minors. So now let's go to triangle-free graphs. So again, we know by Euler's formula that triangle-free graphs, planar graphs, satisfy this nice bound of 2b minus 4. But again, we do not have an analog of Euler's formula for linklessly embeddable graphs. So let's maybe try the same thing. Let's look at K5 minor-free triangle-free graphs. Right, so what if you just look at triangle-free graphs with no Kp minor? Well, it turns out this doesn't actually work. So if you take the complete bipartite graph with 3 vertices on one side and the other side gets large, this graph does not have a K5 minor, but the number of edges is 3v minus 9. So this is much larger than the bound we know for planar graphs. Okay, so this won't really help us in this case. But let me just mention that we can actually prove a tight bound for tight analog, triangle-free analog of these theorems. So these are just all the theorems in the previous slide for no Kp minors. Okay, and also let me just mention that these are all tight. You get the tight examples by starting with a planar triangulation. You just add a few apex vertices. Okay, but now if you add the triangle-free condition, the bound we get is p minus 2 times the number of vertices minus p minus 2 squared. So actually the constant in front of the number of vertices is the same. And we can't do better than this because, again, the complete bipartite graphs prevent us from doing better than this. So all we gain is the constant term at the end here. But this is we can't really hope to get a nice get the tight extremal bound for planar triangle-free linkless embeddable graphs. Okay, and again, this has to break down at some point because asymptotically this is not the right number. You can have more edges, and you can just delete half the edges to get a bipartite graph.
Except for what? Except
so for p equals 8, there was one exception by Jorgensen. For p equals 9, there were 2 exceptions. So these are from the previous slide.
Oh yes, I see. Thank you.
Thank you. Right. So yeah, this is just to say, if you want to look at triangle-free linklessly embeddable graphs, just looking at triangle-free graphs with no Kp minor will not work, even though we have this type bound. Okay, so why doesn't it work? Well, because it turns out the bipartite graphs are the extremal graphs for triangle-free planar graphs, right? So one might guess, because linkless embeddable graphs are the sort of the analog, maybe the complete bipartite graphs with 3 vertices on one side are the extremal graphs for triangle-free linklessly embeddable graphs. Okay, and this is indeed sort of the conjecture that triangle-free linklessly embeddable graphs that are not too small satisfy this bound of 3v minus 9. This was made by McCarty and Thomas a few years ago. So this is still open. But what they can show is that if you strengthen the condition to bipartite, so rather than just triangle-free, if you make it bipartite, then they can show this bound. They can actually show that this complete bipartite graph is the only extremal example. All right, so but still, for this conjecture, we do not know. This is still open. So now let's go back to the planar case and sort of look for inspiration there. So let's make the try to make the statement stronger. It turns out it helps in some cases with the inductive step. Okay, so again, we know by Euler's formula that if a planar graph with triangular faces, T triangular faces satisfy this bound. And the natural conjecture is to sort of bump these up, the 2's to the 3's. So 3v minus 9 plus T over 3. So the conjecture is that linklessly embeddable graphs with exactly T triangles satisfy this bound. And this is a strengthening of the first bound. But so this is of course still open, but what we show is that it's true for apex graphs. Okay, and this is sort of at least some evidence for this conjecture because it seems like all the tight counterexamples come from these apex graphs, where you start with some planar triangulation or planar extremal graph and you just add some apex vertices. Okay, so we still can't show the general linklessly embeddable graphs, but we can show it for apex graphs. Okay, so let me quickly go through the outline of this proof. So the idea is to just take a minimal counterexample, and instead of looking at all triangles, because we know that the graph is apex, let's look at triangles that we have good control over. So let's look at the triangles that are on the apex vertex, which correspond to the edges in the neighborhood of A. Okay, and let's also look at the triangular faces after you delete this apex vertex. So this is, if you add these two types of triangles, that's obviously a lower bound on the total number of triangles in the original graph. And so we want to show this stronger statement. We have a better grasp of how these triangles behave. So we want to show this stronger statement for induction. Okay, but this turns out to be false. So if you start with a complete bipartite graph with 3 vertices on one side and a lot of vertices here, okay, now if you just add this red edge here, BC. So you start with the bipartite graph. You get 3d minus 9. You add this red edge. The number of edges goes up by 1. But the number of triangular faces goes up by 2. And the number of triangles on A does not go up. So this violates this bound. And actually, if you add any of the subset of any edges, any of these green edges, it also violates this bound. Okay, but this is a sort of a very specific example that's close to the extremal example that we would expect. So instead of giving up, we just say, okay, let's just exclude this as an exceptional graph and still try to prove this bound for all other graphs. So that's what we do. We show that a non-exceptional apex graph satisfies this bound. Okay, so now let's try to prove this by induction. So the two main steps here are first to show that there are no triangles on A. Right, so the total number of edges is a number of edges in the planar part, which we have a good grasp of, and the number of edges on A. So, but if you show that the neighborhood of A is independent, then we can bound the degree of A by bounding the size of independent sets in planar graphs. So let's first see how the first part works. First step, how do we show that the neighborhood of A is independent? Well, first, suppose there is an edge here. Then if we delete this edge, we can apply induction in the smaller graph. And when we add back this edge, we introduce exactly 3 triangles that we care about. So that would be nice, except that only works if you started with this 4 cycle. If you have a larger face here, then this induction wouldn't work. So we actually need to prove even stronger statement. So instead of just looking at the triangles, because it doesn't really tell us much about the smaller graph, we actually look at all faces and we define this parameter where we sum over all faces and take 4 minus the size of the face. So the triangles contribute a 1, and larger faces actually contribute negative terms. So this is, again, a strengthening of the statement that we wanted to prove. Okay, and now we have the right strengthening, and the proof goes through very naturally. So again, let's try to show that the neighborhood of A is independent. You delete the edge, so the number of edges goes down by 1, but what happens to the faces? So now we deleted these two faces, but we added this one big face. So what happens to this face parameter? We subtract we subtract the terms for these two faces, and we add this one large face, and turns out this goes down by exactly 2. So we deleted one triangle on A, and exactly 2, we subtracted 2 from this face parameter. So both sides of the inequality goes down by exactly 1. So now that we have the right statement, the right strengthening, the proof is just very natural, very straightforward. Okay, and you just put it together, and the result follows by induction.
Sorry, you have started from the theorem with T, not with TA, but it was 2 pages before, but what is it? It is correct or not? Two table chairs before.
Here. Right, yes. So we exclude these as the exceptional graphs.
So this theorem is correct or not?
So this, as stated here, is incorrect, but this is correct because we exclude these non-exceptional graphs. Right, so we just exclude those graphs and every other apex graph.
So it is correct for non-exceptional.
Right, and the exceptional graphs also satisfy the original conjecture,
also satisfy.
Because they have a lot of triangles that are not faces or on A. So this theorem is true for all graphs, but the way we show it is to prove the strengthening with this one exception.
Thank you.
Okay, so now we know that the neighborhood of A is independent. Okay, and let me just the same argument works to show that if you just look at the planar part, every vertex has degree at least 3. Because if you have a vertex of degree 2 in the planar part, you just sort of do the same thing. You delete the path, you look at the way the faces change, and it works out exactly as we want. So now recall that we're trying to give an upper bound of number of edges, which is a number of edges in the planar part plus the degree of A. So now how do we bound the degree of A? Well, we know that the neighborhood of A is an independent set. So this raises this natural question: what is the maximum possible size of an independent set in a planar graph with minimum degree 3? Okay, so the minimum degree 3 condition is important here, because if you have minimum degree 2 or 1, the answer is trivial. You just take the complete bipartite graph with 2 vertices on one side. You can get all the vertices except 2 as an independent set. Okay, but once the minimum degree is at least 3, it becomes a bit more interesting. It turns out you can only get roughly 2/3 of the vertices. And here's a proof of that. It's a cute little discharging argument. So let's just take an arbitrary independent set, assign a charge of 1 to every vertex in this independent set, so that the total charge in the whole graph is the size of the independent set. Now, for each vertex, you just equally distribute the charge to all the incident faces. This, of course, does not change the total charge in the graph. But now let's look at the charges on the faces. Each face receives how much charge? Well, each face has at most the floor of half vertices that are in the independent set, because independent sets, you can't have edges between them. So you can have at most half, and each of those vertices give you at most 1/3 charge, because they have minimum degree 3. So every face gets at most this much charge. So now we just sum up the charges on each face. The total charge in the entire graph that we started with was the size of the independent set, right, which is just the degree of the apex vertex. Okay, this is at most the sum of all the faces in this parameter here. And because the sizes of the faces are always at least 3, this is always at most this f-2. Okay, and from here you can see that the total charge is actually at most 2/3 the number of vertices, because the number of faces in any planar graph is at most roughly 2/3 of the number of vertices. Okay, but now if we have this, we have a bound on the degree of A in terms of all the faces, and we just plug in Euler's formula and work through all the details, and we get exactly the bound that we want. So that's roughly the outline of the proof. So I think I'm out of time, so let me just skip the second theorem. So again, we had another result that triangle-free graphs with no KP minor satisfy this bound, and this was just a slight improvement on the general KP minor free extremal function. But I'll just skip this proof. So let me just end with some open problems. So again, this extremal function for triangle-free linklessly embeddable graphs is still open. It's kind of sort of frustrating that we can't even prove such sort of simple basic statements about linklessly embeddable graphs, but really because they're very nice topological family of graphs, but we don't have a good grasp of sort of the structure other than this excluded minor characterization. Okay, so again, do you have this strengthening that maybe if you have T triangles, then this band should hold. Okay, so this might help with the inductive step. Okay, and again, the conjecture of Seymour and Thomas that KP minor free graphs, as long as you also impose high connectivity, this Motter bound should also hold in general, because all the counterexamples seem to be these small graphs where graphs conclude along small vertex sets. Okay, and one other open question is, okay, what we have the result for triangle-free KP minor free graphs. What if we extend that to higher girth? So that's also a sort of a natural problem that we don't know yet. So these are just a few open questions that we don't know the answer to, and I think just linklessly embeddable graphs, I just think they're a very neat class of graphs, and it would be very nice to know some more things about them. So I'll stop here. Thank you.
Thank you, Youngho. Let's thank the speaker for talk. 1, 2, 3. Questions? There are some. This last question of high girth, wasn't this question studied already a little bit?
Right. So I mean, asymptotically, it should still be this p times square root of log of p, I believe. Mm-hmm. But for small values, maybe you could do a bit better, and maybe that'll tell us something about linklessly embeddable. So yeah. So this question here, I'm mainly interested in the small values.
Oh, okay.
Yeah, asymptotically, it shouldn't be linear.
Okay. If there are no more questions, let's thank Youngho again.